We're going to venture into the world of soil fertility just a little bit tonight. The title is Soil Fertility and Health, but I think under the confines of our time tonight, we're really only going to get a chance to talk about some of the more important aspects of soil fertility as it relates to small grains, both in grain and forage. So I'd like to start off with a little overview of how recommendations are developed and tested, and then go over what the recommendations are in that Utah State has promulgated over the years for both irrigated and dryland grain and forage, and talk a little bit about rotational adjustments, particularly following alfalfa, as most of us are generally following alfalfa with either corn or small grain rotational crops. And I'll cover some of the recent work that we've been doing, Dr. Yost and Dr. Creech and others in combination over the last, about 8 years or so. So let's delve into how recommendations are kind of developed. This is what we call a rate response curve. Typically what we'll do is in relating what the soil test levels are for various nutrients compared to what we might expect to get in terms of a response in yield. This is the kind of thing that we begin to look at and develop and try to interpret in terms of where the levels of sufficiency or the critical levels are in soils for a given nutrient. And so what we end up with is, as we get increasing levels of a nutrient in our soil solution, the response of the crop goes up over time till we get to a threshold or a limit where we have plenty of soluble and assimilable nutrient in the system that it supports maximum or optimal yields. If you take a look at where universities, public laboratories like the USU Analytical Lab and our extension work will choose recommendation levels that'll be at the point on these curves where you have nearly maximum yield without going beyond in terms of an economically unjustifiable additional amount of nutrient. And we call that kind of the economic optimal levels there, and we'll choose a critical level based on that. Commercial laboratories use the same kinds of curves, the same curves that we use. That comes from the same research that these have been generated. But the critical levels from commercial labs tend to be a little bit further out on the shoulders of these rate response curves. And this is a perfectly reasonable kind of business model to adopt. If you're a commercial laboratory, your interest is obtaining and maintaining clientele and getting return clientele and so forth, working with your lab to take care of your crop needs. And so they don't want to be down further on the curve where you may or may not get the maximum yield and the highest possible returns. But it may cost you a little bit more money in terms of your nutrient inputs. And that's why a university will be at a lower level. Now, it'd be nice if all of the curves were as clean and simple as the one you see here. But what we end up with most of the time, given a different year that we're growing the crop and we're testing its performance, you may have differences in weather, you may have differences in pest pressures, differences in soils and so forth and conditions. And so you get a family of curves like I've depicted here in this particular graph, where we see the amount of a nutrient applied versus the yield, and it'll be a little bit different from study to study. And you end up with critical levels, as you see drawn here, the vertical lines, critical levels for each one of these curves that's a little bit different. And so when you see a recommendation that comes from a university or a commercial laboratory, doesn't matter what, you're going to see a range listed for the recommendation, and we'll see that here in a little bit. We take a look at specific recommendations from Utah State University. So you'll get a range of what is the economically optimum nutrient application depicted, and the same thing you get with commercial recs, but they'll be just a little bit higher typically. In fact, they'll be generally anywhere from maybe 15 to 25% higher because they go out a little bit further on the shoulders of these rate response curves. Again, there's nothing right or wrong about that, but it's a paradigm, kind of the perspective of where a public laboratory like ourselves, being down here at the maybe not the maximum, but the reasonable optimum in terms of economics, versus making sure we don't leave any yield on the table that a commercial lab might target. Again, these are stylized curves. What we really see is data like this. And I wanted to show this to you because you can see how messy life science is in many situations. This is alfalfa yield over here in terms of the percentage of total maximum yield, and the soil test level for phosphorus. I put this on here. It's not small grains, but it's illustrative of a point. You get a lot of point estimates, point values when you're out doing these tests of the performance of the crop versus the level of nutrient in the soil. And one of the things we have to take into account is what our starting points are. We get this kind of a mass of data, and we can draw one of those response curves in there like we had before, and we can kind of try to pick off what the critical levels are going to be down here in terms of the nutrient content in the soil solution. But what we find is as the level of initial nutrient in the soil solution increases, the response, the likelihood of response also increases. And so, as we get lower levels, of a nutrient in the solution, the likelihood of response increases. So, if we take a look at this graph and separate it out into different groupings, where we started out with a higher level of nutrient in the soil down to a lower level of nutrient in the soil. The dotted line here shows you that for a small increment of increase in the phosphorus applied, the likelihood of a response is quite high at low soil test levels. Whereas if we have a higher residual in the system, in the soil system, the likelihood of response is quite a bit less, and maybe even negligible in many cases. And so that's why we're really interested in targeting these critical levels or threshold levels of sufficiency, so we don't encourage the unjustified expense of that additional bit of nutrient applied to receive or to obtain a response in the crop. So with that as background on how these are developed, maybe you have a little better sense of what goes into developing a recommendation. Let's take a look at where we find these. A lot of times it seems like it's pretty much a black box. You send in a sample and you get it analyzed, and the laboratory comes back with a recommendation. It would be nice if, and you can just accept that, and that's fine. But a lot of people have mentioned that they would like to be able to go back and take a look at these recommendations and get more familiar with them and know where to look and find them, so that they can compare when they get a laboratory result from one place or another. What would the USU recommendation be, say, if I got my soil test done at another commercial laboratory? You can go to this particular fact sheet. It's called Understanding Your Soil Test Report. It's in our Digital Commons collections on campus, and you can go to Digital Commons USU and look for document A25. I'm going to, hopefully you're going to be able to see this. I'm going to go to that document right now. Reagan, you can verify whether or not you're seeing that document on the screen.
Yeah, we are seeing it.
Awesome. So this is what it looks like. It's called Understanding Your Soil Test Report. And we tried to put the information down as to where these recommendations come from so that it doesn't seem so much like a black box to you. You can go down through here and it talks about soil tests and soil test reports and what they look like and what's included in them. And then down in the middle of the report, you'll see this box that says click here for a table of soil test interpretations and recommendations. If you click on those, it'll take you to this jump screen here where you can look at the different crops or other settings for nutrient management. And you can choose one of these. Each of these is an active link, and you can go to the recommendation tables that we use in the laboratory when we do a soil test to compare to in order to generate a recommendation for you. So let's go ahead and let's go down here to wheat to start with. We'll choose wheat. And what you'll see is this table here, where you have on the left-hand side over here the different soil tests, phosphorus, potassium, nitrogen, zinc, and so forth. And then you have, from all of that research that's been done on rates and response to levels of nutrient in the soil, you then see it broken down into various categories of nutrient content or the soil test level of that nutrient in your sample. And so for most of ours, the adequate or normal is the sufficiency level. That's where we would think that you have plenty as far as the USU recommendation goes. The additional application of nutrient is not necessary. It's not economically justifiable. Below that, however, we get various levels of need. Everything from very, very low and severe need to kind of a marginal or nearly adequate condition. And so you can compare then. If you get a soil test value, let's say for phosphorus at 8 parts per million, you know that you're in that low category. So what does that mean in terms of recommendation? You slide over to the other side of the table here, and your low B level would say that you would need, in that case, 40 to 60 pounds of P2O5 per acre of nutrient in order to supply adequate amounts for optimal performance of the crop in that particular soil. So you can see where you are. In fact, it's kind of nice to notice that in all of these cases, again, you see a range in the recommendation. When you're between such and such levels, then you apply such and such amounts, a range of possible amounts. Well, if you're in the interest of economics and so forth, wondering if you can use the upper or the lower end of that particular recommendation, you can compare to where you're at in terms of the soil test level. If I'm at the low end of low, then over in the recommendation, I want to be at the high end of application. If I'm at the high end of soil test within that category, then I can probably get away with being at the lower end of that range in terms of the recommendation for the nutrient. And so I hope these tables can maybe provide a little bit more context to the nutrient needs that you see in your soils when you get your soil test results back on these. We'll take a look here at some differences between these in the different crops. But if we go back to the crop table, you can see that we've got several of our grain crops, or small grains. The barley's in there separately as a separate table. Oats is in there separately as a table, and wheat. And then the dryland small grains as a group are also in there. Their recommendations are going to be very different. comparatively, just because we don't have the water to support the use of larger amounts of nutrient in the system. Forage grains will fall into the grass hay category. And we'll take a look at some nuances to maybe some of the work that's been recently done on that. But let me go back now to the PowerPoint. This is kind of a summary. We just pulled some of the information out of those different tables so that you can see kind of the comparison. So irrigated wheat in terms of, yield goals and things like that, you can be upwards of 140 bushels per acre. And so you could be as high as maybe 170 pounds of in terms of base and recommendation for the crop. If you don't have that high yield goal, a little bit less, but in between, if your yield goal is somewhere in between, then you can adjust by 2 pounds of nitrogen per bushel per acre. And you can see that the barley has a separate table, and it's a little bit less in terms of overall need. That's why there's some nuances to each one of these. Dryland grain, you'll notice in terms of nitrogen application, you're only about a third to a half of the nutrient requirement in those settings, just because of the differences with respect to water and water availability in the process. And then we have some other adjustments that typically need to be made to our recommendations, particularly if we're in some kind of a rotational situation where we're following a legume crop like alfalfa. In the past, we've noted that there's about 100 units of nitrogen in terms of credit to a previous alfalfa stand for all crops that might be grown in rotation following that alfalfa. But let's go to some interesting newer data that's been generated over the last several years in response to revisiting these recommendations to make sure that we're in alignment with these credits that we've used for so long. Here you see a table from some recent work, Dr. Yost, Dr. Creech, myself, and others with our students in looking at the rotational adjustments to grain production with following alfalfa. And this is 12 different or 18 different sites around the state in 2018 and 19. And you can see over on the far right-hand side that the requirement for nitrogen following alfalfa, and here are the stand ages of the alfalfa that came out previous to the grain crop, that only about half of the sites were actually responsive to added nitrogen. In fact, if the soil test level for nitrate was less than 17 parts per million, we got a response. Where it was not, we generally did not get any response at all. And so not only do we have an end credit to the previous alfalfa crop, but we also need to take a look at what the actual residual nitrogen is left over in the system. And if we're greater than 17 parts per million, we typically do not need to add additional nitrogen following alfalfa. And that's for grain. In many cases, grain was responsive, but we need to pay attention to what's actually in the soil. In terms of,
sorry to interrupt. Yeah. We're about up with time, so if you could find avenue to wrap it up.
This is my last table here, just to kind of follow up on the forages. Forage is a very different animal in terms of its response to nitrogen following alfalfa. In 12 sites in 18 and 19, only one was responsive. There was enough nitrogen following alfalfa to supply maximum forage production on small grains, regardless of where we found it in the state. The only responsive site was on a very old, greater than 10-year stand. And so take home there is apply nitrogen only if your stand is greater than 10 years old on forage grains. And that's consistent with other data. I won't go into the Davis, but it's consistent with other data around the country in various similar tests. So with that, I'll be done tonight.